Hello and welcome back to the course on artificial intelligence. Today we are finally talking about Qlearning. Alright, so we've already got this equation, the Bellman equation, which we've added lots of components to. We've got the reward here, which can be not just at the very end, but it can be at any given step. We've got the discount factor, we've got the probability, because now we're looking at Markov decision processes, and here we've got the probability of ending up in different states regardless of what action we take, or actually given the action we take, there can be multiple states that we can end up in, and then we've got the value of the next state. So you can see it's kind of like a recursive function and so on. But you probably still have one question. The question is, where in all of this is the letter Q? Why is it all called Qlearning? So where's the Q? And that's the question that we're going to be answering today. So far, we've been dealing with values, the value of being in a certain state. And now we're going to look at how Q fits into all of that as well. So here we've got two examples. On the left is what we've been doing so far. Our agent has been analyzing, okay, I'm over here. This is a Markov decision process, so it doesn't matter how I got here. The rest of the environment doesn't care of the steps that it took me to get here. From now on, I have to make the optimal decision where to go, here, here, or here, based on the current state and all the future states that come from here, but not from the past. And so he can see that there's three options. There's state 1, state 2, state 3, and based on his experience, he has calculated the values in these states. And now he's going to, using the Bellman equation, so even that though this is a stochastic process, so he knows that he'll go here, but there's a chance that he'll go left or right, and so on. So based on these values, he's going to make a decision. That's what we've been doing so far, and that is totally the legitimate approach here. But now we're going to modify it a little bit. We're going to take the same exact concept, same exact problem, but here, instead of looking at the values of each state that he can end up in, we're going to look at the values or the value of each action. So we're not going to use the letter V anymore because V is for the value of the state. We're going to use Q. And you might have a question, why the letter Q? Well, Q, some people speculate that Q, well, I read this, I think, on Quora. Somebody mentioned that Q is because of quality. But at the same time, I couldn't find any other references to that, so it might not be because of that. It might be just because that's the letter that was used at the time, and now it became super popular because it's all called Qlearning because of that. So no exact reason why it's called Q, but nevertheless, at least it helps us distinguish between V and Q. So Q here represents, rather than the value of the state, it represents, let's go with quality, it represents the quality of the action. It represents, okay, so I've got 4 actions. What are the different qualities of these actions? What is the or the value of the action or the quality of the action? Which action is more lucrative? So I need a metric telling me, all right, how do I quantify this action? And then I can compare them. And that is exactly what Q is. And so here he's got 4 possible actions. As always, go up, right, left, or down. And based on the action, there's going to be a formula which tells us the quantifiable value of that action, which we're calling the Q value of that action. So let's have a look at how we're going to derive this formula for Q. How does it actually relate to V? Because as you can imagine, because actions lead to states, there has to be some sort of link between the two. Right? We've already determined how to calculate this, and we're pretty good at it. We know how to use the Bellman equation in very different environments with lots of different complications. Well, let's leverage that knowledge to understand how we can now calculate Q in order to make the same predictions. Because as you can imagine, the environment doesn't change depending on what approach we use. The environment is going to be the same regardless. So therefore, this approach and this approach should always give the same result. And therefore, that's another reason why these two should be linked. So let's have a look. So here's our V approach, where we're just going to look at the value of any given state, this state, any other state. And here we're just using the letter S here because that's the current state. And so therefore, the terminology will be the same in both equations. And here we're using QSA. Q is of the state S and the action A, because action is up, but in which state did we perform that action? We performed that action in state S. Okay, so now we're going to write out the Bellman equation for the first approach. As you can see here, we've got V of S, so the value of any given state S, is the maximum of the reward that you get. So maximum based on the actions. So you have three. In this case, you actually have 4 actions. So maximum out of all the possible actions, and then of this part, which we've already discussed many times. So this is our reward that we get from performing that action in that state, plus a discounted factor multiplied by the expected value of the new state that we're going to be in. An expected value because it is a stochastic process. We don't know exactly for sure that we're going to end up over here. We might end up on the left or the right with a certain probability. That's why these probabilities are in here. All right, so that's our value. And now let's look at Q. So Q is going to be defined. We're going to use this to define Q. So let's say the agent from this location, from this state, performed the action up. What is the Q value going to be equal to? Well, first of all, let's see what he'll get in return. For performing this action up, first thing that you'll get is a reward, right? That's no doubt about it. There's going to be some sort of reward. It might be 0, but we know that the way this reinforcement learning process works is that sometimes for performing certain actions from a given state, there's a reward. So we're going to add that in here. And then we're going to add, what are we going to add? Well, let's think about it. What is the next thing that happens after he's gotten the reward? Well, the next thing that happens is that now the agent is in a certain state. He could end up here with a 80% probability or some probability, but actually he could end up here or here. But wherever he ends up, now we already have a quantified metric for that state he's in, and that is actually the V value of that state. But because he can end up in many different states, in 3 of the possible different states, we have to look at the expected value of the state that he'll be in. And so we're going to add that in. We're going to add, of course, the discounted factor as we previously had, because that is somewhere in the future. And then we're going to add the sum of across all possible states that he could end up in by taking this action times the probability. So what we're saying here is that, okay, so by performing an action, you're going to get a reward plus, which is a quantified metric, plus you end up in a state. We don't know which one. It could be here, it could be here, it could be here. But here is the expected value of the state that you're going to end up in. And now we're going to multiply it by discounting factor because that is 1 move away. So that is our Q value for performing this action. And what you will notice here right away is that the Q value is actually exactly identical to what's inside these brackets over here. And why is that? Well, if you think about it, here we're taking the maximum of the result we'll get, the maximum across all possible actions. So we've got 4 actions, and we're taking the maximum across all possible actions of the result that we'll get by taking each of those actions. And in Q, we're defining, interesting, what will we get by taking a certain action? So if you think about it, it makes sense that the value of a state, so for instance, this state, is the maximum of all of the possible Q values, right? So here in this state, by being in the state, the agent has 1 Q value, 2 Q value, 3 Q value, 4 Q values. So he has 4 possible Q values. Well, the value of this state, it makes sense that the value of the state is the maximum of all of those 4 Q values. And that is exactly what we can see here. That's a good confirmation of this new formula that we derived. If that wasn't the case, if that didn't match up, then we would have questions. We'd be like, so why doesn't it match? Why doesn't it match up if Q value is a quantified metric of performing an action, and V depends on is the maximum of the possible results of the 4 actions that he can perform. Hopefully that makes sense, and that confirms the formula that we've just derived. And now we're going to make it even more interesting. We're going to get rid of the V entirely, because you can see here you got V is a recursive function of V. So, and then we got V, and then V, and then V, and then V, and so on. So you can express this V through all of the following V's, the most optimal V's that will come up. Here, we're expressing Q as a recursive function of V, or as a function of the next V. And then we'd have to plug in this V, and then we'd get back to the V. So what we're going to do is we're actually going to take this V, and we're going to replace it with Q, right? So let's have a look at that. We're going to take this V of the next state, and we're going to plug this into that formula over here. And as you can see now, so this part doesn't change, this probability doesn't change. But as we just discussed, V of S is the maximum by all actions of Q of S and A, right, over here. So that's what we're going to replace in here. So we're going to say a maximum of course, it's the new action, the action that we're going to take, because here we've got V of S prime. So here now we've got the maximum across all A primes, so the actions that we're going to take from this state or from whichever other state we end up in. But the action that we're going to take from there, and a maximum across all those, and the maximum is of all of the Q values that are available to us in that new state S prime, comma A prime, and that's the action. So there's going to be another 4 Q values there. So now, as you can see, let's go through that again. So as from what we derived, as from what we discussed, just through logic and intuition, so that we can see that V and S are actually, V of S and Q of S and A are linked. V of S is the maximum across all actions of Q of S and A. You can see it right here. So this part is identical to this part. And then we're going to leverage that, and we're going to replace this bit with V at S from here, but not this exact formula. We're going to take this internal part, and we're going to replace it with Q of an S and A. So we're going to plug that in here, and this part is going to be Q of S prime A prime. So maximum of Q by across all A primes of Q S prime A prime. And now we have our formula. So now we have a recursive formula for the Q value. So now the agent can think, what's the value of this action? What's the quality of this action? What's the Q value of this action? Well, it depends on the reward I get in the immediate step after that. Plus, it depends on the discounted factor times the maximum of all the possible Q actions in that state. But I don't know if I'm going to get there. So I need to also look at that state and that state. And that's why we have this expected value over here. So we have this sum, probability times the maximum, and that's our expected value. So very similar formula, as you can see, but this time we're expressing things through the Q values. And that's why this whole algorithm is called Qlearning, because this is what is looked at. This is what the agents actually use. They don't look at the states, they look at their possible actions, and then based on the actions, on the Q values of the actions, they will decide which action to take. So they'll just look at the maximum Q value in this given state. It has 4 actions. What is the best action to take? So it can compare, instead of comparing the different states it can end up in, it's going to compare the possible actions that it currently has. Then by finding the optimal one, it's going to take that action, and then it's going to repeat that process, and so on. So now you can see how all of this comes together, how the reward, the discounting factor, the stochastic Markov decision processes, and the V values and the Q values all come together in order to give us this one super powerful Bellman equation for Q values, which we can now apply and let our agents learn how to beat the environment. And so that is a intuitive explanation of what's going on. I know we went through the formulas, but it is necessary because this is like our formula that we've been going through this whole chapter. And I think it's a good transition from V to Q, and it illustrates how they're linked between each other. And if you'd like to get a bit more of a rigorous approach, mathematical approach, and like you see the mathematics behind it and learn a bit more about Q values and how they work, then we've got some additional reading for you. This paper is called Markov Decision Processes, Concepts and Algorithms by Martin van Otterlo, 2009. So you've got the link here as always. And here you can read in a bit more detail to understand all the nitty-gritty behind Q values and so on. And now that we've discussed all of these things relating to the Bellman equation, now we are ready to look at something more complex, such as this paper, in order, if we want to get some additional information on this, in order to kind of get a deeper understanding. But even if you don't read through this paper already, you should have a good working knowledge of what Qlearning is all about and how agents come up with the actions that they need to take in a certain environment. So I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy AI.